Hi guys, welcome to the next section, Putting Data in Place, Supervised Learning for Predictive Analytics. Now, we move on to the first video of this section that deals with supervised learning for predictive analytics. Let's look at supervised learning for predictive analytics. Depending on the nature of the learning feedback available, the machine learning process is typically classified into three broad categories: supervised learning, unsupervised learning, and reinforcement learning. A predictive model based on supervised learning algorithms can make predictions based on a labeled dataset that map inputs to outputs aligning with the real world. For example, a dataset for spam filtering usually contains spam messages as well as not spam messages. Therefore, we could know which message in the training set are spam and which are ham. Nevertheless, we might have the opportunity to use this information to train our model in order to classify new unseen messages. This diagram shows the schematic diagram of supervised learning. After the algorithm has found the required patterns, those patterns can be used to make predictions for unlabeled test data. Let's start from the very simple linear regression algorithm. We have seen that the regression is a type of supervised machine learning for predicting the continuous valued output, basic Python, and linear algebra for predictive analytics, and never driving it. This awesome machinery begs to manifest itself in the real world. Fortunately, many datasets are available online to test your newfound knowledge of regression. Kaggle contains all types of large-scale data for machine learning competitions at this link. Therefore, in this section, by defining a set of models, we will see how to reduce the search space of possible functions. Moreover, TensorFlow takes advantage of the differentiable property of the functions by running its efficient gradient descent optimizer to learn the parameters. To avoid overfitting our data, we regularize the cost function by penalizing larger value parameters. In TensorFlow, operations such as addition and multiplication take two inputs and produce an output. In contrast, constants and variables do not take any input. Now, we will use linear regression for movie rating prediction. Now, the first task is downloading the Fandango's rating dataset from GitHub at this link. It contains every film that has a Rotten Tomatoes rating, an RT user rating, a Metacritic score, a Metacritic user score, IMDb score, and at least 30 fan reviews on Fandango. The dataset has 22 columns that can be described as film, which is name of film, Rotten Tomatoes user, Metacritic, Metacritic user, IMDb, Fandango stars, Fandango rating value, RT norm, RT user norm, Metacritic norm, Metacritic use nom, IMDb norm, RT norm round, RT user norm round, Metacritic norm round, Metacritic user norm round, IMDb norm round, Metacritic user vote count, Fandango votes, and Fandango difference. We've already seen that a typical linear regression problem using TensorFlow has the workflow that updates the parameters to minimize the given cost function of Fandango's lopsided rating curve. Now, let's try to follow the figure and reproduce the same for the linear regression. First, we will define this code to ignore the warning. Next, we will import the required libraries. After that, using these lines of code, we will read the dataset and create a Panda data frame. So, if you look at the preceding data frame carefully, there is a typo that could cause a disaster. From our intuition, it is clear that Metacritic user nom should have actually been Metacritic user norm. Let's rename it to avoid further confusion. Moreover, according to a statistical analysis at this website, all the variables don't contribute equally. The columns have more importance in ranking the movies. Now, we will check the correlation coefficients between variables before build the LR model. First, let's create a ranking list for that. This function computes the Pearson correlation coefficients and builds a full correlation matrix. Let's call the method to plot the matrix. As you can see, this correlation matrix shows correlation between considered features using the Pearson correlation coefficients. So the correlation between Fandango and Metacritic is still positive. Now, let's do another study by considering only the movies for which RT has provided at least a 4-star rating. The output is the correlation matrix on the ranked movies and RT movies having ratings of at least 4, showing a correlation between considered features using the Pearson correlation coefficients. This time, we've obtained anti-correlation between Fandango and Metacritic with the correlation coefficient minus 0.23. This means that the correlation of Metacritic in terms of Fandango is significantly biased toward high ratings. Therefore, we can train our model without considering Fandango's rating. But before that, let's build the LR model using this first. Later on, we will decide which option would produce a better result eventually. Now, we will prepare the training and test sets. Let's create a feature matrix X by selecting 2 data frame columns. Here, I have used only the selected column as features, and now we need to create a response vector Y. We are assuming that the IMDb is the most reliable and the baseline source of ratings. Our ultimate target is to predict the rating of each movie and compare the predicted ratings with the response column IMDb norm. Now that we have the features and the response columns, it's time to split data into training and testing sets. If you want to change the random state, it helps you generate pseudo-random numbers for a random sampling value to obtain different final results. If a random state is none, a randomly initialized random state object is returned. If random_state is an integer, it is used to seed a new random state object. If random_state is a random state object, it is passed through. Now, we need to have the dimension of the dataset to be passed through the tensors. We include an extra dimension for independent coefficient. And so, we create an extra column for the independent coefficient in the training set and test feature set as well. So far, we have used and utilized the Pandem data frames, but converting it into tensors is troublesome. So instead, let's convert them into a NumPy array using these lines of code. Now that we have all the training and test sets, before initializing these variables, we have to create the placeholder for TensorFlow to feed the training sets across the tensors. Let's add some bias to differing from the value in the case where both types are quantized. Let's create an optimizer for the objective function. We will now initialize the global variables. Here, we are iterating the training 50,000 times and tracking several parameters, such as means square error, that signifies how good the training is. We are keeping the cost history for future visualization, and so on. Finally, we evaluate the MSE to get the scalar value out of the training evaluation on the test set. Now, let's compute the MSE and RMSE values. Now that we are not considering the Fandango's stars, I experienced the result of MSE and RMSE as 0.42 and 0.65 respectively. Using these lines of code, we will observe the training cost throughout iterations. This is the output. This graph shows that the training cost becomes saturated after 10,000 iterations. This also means that even if you iterate the model more than 10,000 times, the cost is not going to experience a significant decrease. Using these lines of code, we will evaluate the model. This shows the predicted versus actual rating using LR. We can see that the prediction is a continuous value. Now, it is time to see how well the LR model generalizes and fits to the regression line using these lines of code. This is the output that we will get. The graph does not tell us that the prediction made by the LR model is good or bad, but we can still improve the performance of such models using layer architectures such as deep neural networks.